So if we combine what we know about resonance with what we know about formal charge, this is going to allow us to look at questions where we need to identify the best resonance structure. So this will allow us to identify the best resonance structure. The best resonance structure will be the one that most closely resembles the actual structure of the molecule. And in your analysis of a best resonance structure, what you want to consider is a structure where you have all formal charges at 0. That's going to be best. Then we'll consider structures that have small formal charges. And the only formal charge that's considered to be small is going to be a plus or minus 1. Number 3 says that when formal charge cannot be avoided, negative formal charge should go on the more electronegative atom, and positive formal charge should go on the less electronegative atom. So let's look at an example of carbon dioxide, CO2. You may already know the structure of this molecule, but when we follow all of the rules for drawing this structure, there's more than one way that we can complete carbon's octet. So if I look at this example, my carbon is going to contribute 4 valence electrons to the structure. I have 2 oxygens that will each contribute 6 valence electrons to the structure, giving me a total of 16 electrons. As I follow my rules, my carbon goes in the middle and my oxygens become my outer atoms. As I complete the octets for my outer atoms, that's going to use all 16 of my electrons. So this is the structure that I have when I complete step 3, and this is where I've completed the addition of all of the electrons into my structure. So now if I look at step 4, there are no electrons to put on that carbon, so I have to work with the electrons I already have in this structure in order to complete carbon's octet. Carbon sees 4 electrons currently in this structure in the form of the 2 single bonds. Carbon needs 4 more electrons. And make sure you do this systematically. So when I look at this structure and I try to see how I'm going to complete this structure, my carbon needs 4 more electrons. So one of the ways that I could complete carbon's octet is by taking a lone pair from the oxygen on the left and giving it to the carbon, a lone pair from the oxygen on the right and giving it to the carbon, and that's going to give me this structure here, which I'll call structure A. Structure A follows all of the rules. Structure A looks symmetrical, so we like that about structure A, but let's look at the other possibilities that we have. In the same way that I could take 1 lone pair from each carbon, there's nothing that prevents me from taking 2 lone pairs from a single carbon. So in the next structure, I can take this lone pair and this lone pair and give the orange lone pairs to the carbon, and that's going to give me this structure here, which I'll call structure B, where I have a carbon-oxygen triple bond and a carbon-oxygen single bond in the structure. This is a structure that follows all of the rules for Lewis structures. If you're clever, you'll realize there's one more structure that I haven't drawn on the paper yet, and that's where both of the lone pairs come from the oxygen on the right, so it's going to be a structure that's equivalent to structure B, and it's going to look like this. And we'll call that structure C. Okay, structure B and structure C are going to be equivalent resonance structures of one another. Now, these structures, A and B, are not equivalent resonance structures. So that means that I need to use what I know about the best resonance structure and my formal charges in order to understand what the final and best Lewis structure for carbon dioxide is going to be. So pause the video and calculate all of the formal charges for all of the atoms in structure A and structure B, and use that information to decide who the best Lewis structure for carbon dioxide is going to be. So that as you calculated all of those formal charges, in structure A, you should get a formal charge of 0 on both of your oxygens that have 2 bonds and 2 lone pair. You should also get a formal charge of 0 for your carbon that has 4 bonds and 0 lone pairs. In structure B, you should get a formal charge on this oxygen with 1 lone pair and 3 bonds. You should get a formal charge of +1. On my carbon that has 4 bonds and 0 lone pair, you should get a formal charge of 0. And on this oxygen here that has 3 lone pairs and 1 bond, you should get a formal charge of -1. If you calculated all of the formal charges in structure C, you would get the same pattern of formal charges as we did for B. This one would be -1, 0, and +1. So for both structure A and structure B, the sum of our formal charges does add up to the overall charge of the molecule, which is 0. But when we look at the charges, in A, we have a structure that has all formal charges at 0. That's a good thing. That means that all of our atoms see an appropriate amount of electron density. In structure B, we have a positive formal charge on this oxygen, a negative formal charge on this oxygen, which tells us that this one sees a little too much electron density, this one sees not quite enough electron density. So while we can have oxygens that exist like this in valid Lewis structures, for carbon dioxide, it's going to be structure A that becomes our best Lewis structure, because when we consider all of the formal charges, all of our formal charges in this structure are 0, making it our best Lewis structure. This will be the structure that most closely resembles the actual structure and the behavior of carbon dioxide. At the bottom of your page, you have another example. OCN- is the isocyanate ion. I want you to work through this structure on your own. There are 3 resonance structures that you can draw that follow all of our rules for Lewis structures. I want you to draw all 3 of these structures, do an analysis of your formal charge, and then determine the best structure for the isocyanate ion. Pause the video and determine the best resonance structure for the isocyanate ion. So for the isocyanate ion, when you start by adding up the total number of electrons, you'll get 15 based on the atoms that are in the structure. You'll need to correct the electron count because this is a negatively charged ion, and you get 16. For the connectivity, we know that carbon is in the middle, bonded to the oxygen and the nitrogen, and this is the structure that we get at the end of step 3. As we move through the rest of the steps for resonance structure, there are 3 ways that we can complete carbon's octet from this structure. Pathway A in orange has us complete carbon's octet by pulling 4 additional electrons from the oxygen to give us this structure here. Structure B has us complete carbon's octet by pulling 4 additional electrons from the nitrogen to give us this structure here where we have a carbon-nitrogen triple bond. And structure C has us do one of each. We pull 1 lone pair from the oxygen, 1 lone pair from the nitrogen, and we end up with 2 double bonds that we see here. All are valid Lewis structures, all follow the rules as we've laid them out in this class. In order to understand the best of the Lewis structures, we have to calculate formal charge. For structure A, my oxygen has a formal charge of +1, nitrogen has a formal charge of -2, carbon has a formal charge of 0. In structure B, oxygen has a formal charge of -1, carbon has a formal charge of 0, nitrogen has a formal charge of 0. In structure C, oxygen has a formal charge of 0, carbon's formal charge is 0, and nitrogen's formal charge is -1. So that as I consider all of these formal charges, there should be one structure that jumps out at you as the worst of the structures, and that would be structure A. And that has to do with the fact that we have this formal charge of a -2 on our nitrogen. So this is going to be the worst structure. When we look then at structure B and structure C, the difference is that in B we have a formal charge of -1 on our oxygen, and in C we have a formal charge of -1 on our nitrogen. And we know from our rules that it's better to place that negative formal charge on the most electronegative atom. So that means that it will be structure B that is our best resonance structure that we can draw. It will be the structure that contributes most to the resonance hybrid, most closely resembles the behavior of the isocyanate ion. Structure A is our worst structure, and that will be the structure that contributes least to the resonance hybrid and does not really resemble the behavior of the molecule at all.